You're live.
So since we have no one down the coast, all right. So I have a few more iterative methods that I want to cover, and when I was writing notes for them, I've actually the notes are up. So I've made some additions to chapter 5 after I covered the gradient section. So I've covered 3 more iterative methods there, and I will get to that stuff. But it turns out I can't do it yet because all of those other iterative methods require some coverage of some aspect of least squares problems. And I was going to do a little of that at some point anyway, but now my hand has been forced. So if you're following along in the notes, I'm actually going to make a digression this week to stuff from chapter 6, so 6.1 and 6.2. Those are pretty long sections, and I won't be able to cover all of them, but I just need bits and pieces. Anyway, and actually, I used to cover chapter 6 as part of 610 all the time. I just wanted to have more on iterative methods, or anything on iterative methods. So, as a result, you guys get both. So, it's actually a better deal for you. Okay, so we'll see how much I can get from 6.1, 6.2 this week, and then next week, I'll shift back to some iterative methods before leaving that stuff altogether, to finish the semester with eigenvalues. Oh, Kilia. Yeah, I got your email. I didn't expect you to be here.
Just sign language, it's all good.
Okay, I'm leaving tomorrow, so I'm gonna be here today, and then I have to teach tonight, but not Wednesday.
Ah, gotcha. Okay.
Yeah.
I should read my
Did
emails.
you
I
get 2 emails?
Yes, I did. Yeah.
Okay.
So, okay, I need to read my emails more carefully. Okay. All right. So I was saying, if you're following along the notes, I'll be getting in chapter 6. The full rank least squares problem. So, the problem to solve is the following. So consider this kind of system of equations, ax equals b, except this time, instead of A being an n by n matrix that's invertible, A is n by n. M is strictly greater than n now, but the rank of A is equal to n. So in other words, what I'm saying is the columns of A are at least, they're still linearly dependent. It's just that now those columns are too large. All right. So what happens in this case is a solution to the system X exists if and only if the vector B belongs to the range or a column space of A. Now, before when A was an n by n invertible matrix, this was assured, but now it's not. So it's possible that we might not be able to solve this system Ax equals B exactly. So what we're going to look at is, what if this is not the case? What if your right-hand side vector B is not in the range of A? So we have, there's no exact solution. So we're going to change our goal. Instead of trying to find x so that A times x is exactly equal to B, we're going to try to make A times X as close to B as possible. So we have a way of measuring closeness that's using vector norms. So I want to minimize the norm of B minus AX. So we're going to find X that makes this quantity as small as possible. Now, the first question to tackle is, which norm? I haven't specified a norm yet. Different norms lead to different complexities into how you perform a minimization. The norm that we're going to use is the 2 norm. The reason for that is this norm is differentiable. Now, why does that matter? If I try to choose a norm and I want to minimize this norm, why would I care about whether it's a derivative or not? How would having a derivative help me? What?
You're minimizing.
Yeah, how do you find the minimum of a function? You take the derivative, set it equals 0, or gradient. So having a derivative helps. Now, what's called L1 minimization, minimizing the 1 norm, that's actually an active research area now, but we will get into that. Now, what is the vector 2 norm? That is the square root of the sum of squares of all the components. So what we want to do, effectively, is minimize the sum of squares of the components of this vector. So that's where the term least squares comes from. So we're trying to make the sum of squares the least. Okay, now, how are we going to go about doing that? I'll actually talk about 2 approaches, one more than the other. It's good to be aware of both of them. So the first approach is actually one that's, even though I was talking about derivatives, I'm actually going to do the calculus-based approach later. So it turns out that's really the one that we're less interested in. What we're going to look at is orthogonal transformation. Okay, so we're going to use the fact that if you take a vector and multiply it by an orthogonal matrix, then that does not change the 2 norm. So what I can do is, I can take this vector, b minus ax, I'll multiply that by an orthogonal matrix, so its magnitude is preserved. But I want to choose an orthogonal matrix in such a way that this quantity will be easier to minimize. So what I can do here is use what is called the QR factorization. So that's a new factorization in addition to ones we've seen already, like LU and Cholesky and LDLT. So QR factorization has this form. Well, there's actually 2 forms. The first one we'll call the full QR factorization. And that's the one we're going to use most of the time. So A is m by n, and we write the product of the m by m matrix Q, and then an m by n matrix R. Q is orthogonal, and R is upper triangle. And I'm going to break Q and R down. So the way the QR factorization is normally computed is we have n columns up front here that form Q1, and then I have m minus n columns that form Q2, so the rest of Q. So this is Q right here. And then R, I'll break down into an upper triangular matrix R1 that is n by n. And then below that, we just have zeros. So it turns out, if I carry out this multiplication, what I would really get is Q1 R1. So I have actually two factorizations. So here we have a full square Q that's m by m, and then R has the same size as A. Over here, Q1 has the same size as A, and R1 is a square matrix, so it's the opposite. Okay. Now, what can I say about any of these matrices? Well, first of all, R1 is upper triangular, and because A has linearly independent columns, R1 does too. So not only is it upper triangular, it is invertible. So that makes things easier. And the columns of Q1, those form a basis for the range of A. Whereas Q2, that covers the orthogonal complement of a range of A. I covered orthogonal complement quite some time ago. If you have a subspace, then your orthogonal complement is a set of all vectors that are orthogonal to the ones in that subspace. All right. So this alternative form of a QR factorization, Q1R1, is called the thin or economy size QR factorization. Okay. Now, what can be said about the QR factorization is just like the LU or Cholesky factorization, it is unique. Also, every matrix of this kind that we're considering that's n by n and has n linearly independent columns, the QR factorization is guaranteed to exist for all such matrices. On Wednesday, I'll be getting into different approaches for computing it, and so those tools that we use for that are transformations somewhat like row operations, except they're orthogonal. And we'll be using those quite a bit for the rest of the semester. So that's one way of getting QR factorization here, but also solving these squares problems like this. Okay. Oh, my Skyper just texted back and said, okay, yeah, so she's not making it, but we're filming, so we're okay. Where did my water go? I left it in my office, didn't I? Yep, I did. Okay. BRB.